Good afternoon. I'm Hanna from the Bartlett School of Architecture, and I'm very pleased to be finishing up the DCIO conference this year. I'm going to talk a little bit about collaboration and creativity, but particularly about how the different types of machine learning we might do have parallels with the kinds of modeling we do in computational design and so on. Obviously, when we deal with a design project, a complicated design project, one of the big issues, of course, is that we have very different sets of data, lots of data in many cases, but very different formats, and they're held by different parties, and they all have to communicate with one another. This is often quite a big problem, and it's the kind of thing that is also faced often in machine learning situations. So often there's a case where you've got inconsistent data provided by many different people. An example might be data collected for learning from mobile phones, for instance, by a central server. Each user might be coming in and off the network. The data might be very different. They may be providing data at different times, it may be different sizes, and of course each user is different as well. So you've got all of these inconsistencies with data that you have to manage. And the standard machine learning process, of course, would be to collect it all on a server and run it through a big model. But of course that is quite intensive in terms of the bandwidth and in terms of processing. So federated learning is one method that's become quite popular recently. I'll just briefly go through a very diagrammatic way of explaining it. You've got a statistical model that's held on a central server. This is the untrained machine learning model that's sent out, first of all, to all the nodes, transmitted to them. Now, each of those nodes then is able to collect data, and then it trains that model individually. So the server centrally doesn't do anything at this point. All of the models are being trained at the nodes. And of course, the data is different, so the training of the models all have different results from one another. But at another stage then, the server then gets the models back, they're transmitted back to the server, and the server, the central server, then pools these together, usually by some sort of averaging. So it comes up with a combined model that takes into account all the things that are learned at the various nodes. Now, of course, not all the nodes need to be on the network at the same time. Not all nodes have to provide the same amount of data. It's very good for privacy, data privacy and ownership, because none of that data ever has to be sent back to the central server. Each node can keep its data, doesn't have to share it with anything else, so it can retain it. It allows processing to be distributed. It doesn't all have to take place in the center. Computational load doesn't have to be all at the center. It can be much more efficient because the computation itself can be distributed. And of course, the bandwidth is improved because you don't have to transmit all of the data back and forth. You just have to transmit the updates to the model. Typically, this is just a series of changes in gradients and so on, which takes up a lot less bandwidth. So this is very beneficial in some ways. And of course, as a machine learning model, it may start to sound familiar when we think about the sort of federated models that we have in BIM applications as well. You've got a series of models, each of which does its own thing. They don't have to be entirely consistent with one another, but they have to be worked on individually and then brought back together. The way of doing that is that you have to have some sort of standards usually. In the machine learning case, you might have the statistical model that's sent out and everyone operates on that model, even though their data are different. In the case of, say, CAD and BIM, you might have industry foundation classes that allow everyone to talk to one another using a standard language. So these are very efficient and very similar ways of dealing with different types of data. But sometimes we can't have standards. So there's another way of looking at this in which we don't actually standardize our language. What happens if the categories we're using are fundamentally different? So this is just a short MSc project, Johan Viesinger's project on machine learning and transfer learning in particular, where there's a series of images here. You can see some of them are images of architectural drawings, whether CAD or sketches, but a lot of them are photographs, either of architecture or other things as well. Scenes, flowers, cats, dogs, and so on. And in many cases, the categories we have are not the same. But we may not have, in a machine learning application, particularly if we're using deep learning, convolutional neural networks or something that needs a lot of examples of data, we may not have enough within the category we're dealing with. We may not have enough architectural drawings to train it sufficiently. So the question here is, how much can we learn from these other categories? Can we learn enough about flowers or enough about architectural drawings from flowers and cats and dogs and all these images that are really quite plentiful, freely available on the internet? Can we learn enough from those about what makes an image that we can then use that information later in a completely different setting, in architectural drawing, for instance? And it turns out we can. So in the case of a convolutional neural network or other deep learning, what happens in the convolutional layers is that the network learns basic ideas about how an image breaks down. It learns filters that give you information about the basic visual properties in an image. Now, this in principle is pretty much the way our visual system works as well. Our eyes, our retinas, the neurons in our visual system are good at breaking down images so that we can recognize certain things about them. We can recognize points of contrast or horizontal or vertical lines within them. Very basic image-based things that then can be applied to recognize higher level patterns. But in the case of a neural network here, we've got the convolutional layers that do that sort of thing, and then they pass their information on to another part of the network that usually does the classification, the sort of fully connected feed-forward perceptron type of thing that you can see in the bottom of this image here. Different types of the network do different things, but the portion of that network that's trained on recognizing images quite generically can then be taken from one context, learning cats from dogs, for instance, and taken out and put in another type of network, and then be taught to do something else useful, like recognize architectural images. In many cases, this is the sort of thing that we need to do. So in this project, for instance, by Zihan Huang and others that we're doing in the area of facilities management, the idea is to get a machine vision system to monitor the state of various components of a building. Now, there aren't necessarily enough images of that particular type to train the whole network, but we can use pre-trained networks on other types of images, transfer that by taking part of the network and then transferring it to another one, and then get quite a good way to understanding and classifying both the types of these images and the various states of their elements so that we can monitor the buildings. In other cases, this work by Dumitru Stefanescu, the origin of Speckle, really was to look at the various different types of objectives that different stakeholders have and how those might be reconciled in a system. Now, those of you who were here last year are probably familiar with this. Dimitri presented this with Paul Poinet and others. And the model for Speckle, of course, is very unlike that central hub in which we have one standard for communicating. In this case, each node might have their own different standard, their own different representational scheme, but Speckle sits in to translate data from one to the next. So instead of having that central hub and one central standard of language, you can have a much more distributed network where each node only sends the data that's relevant to the next node on, and they can communicate amongst themselves. So it's a very different system. On the top, you've got this centralized hub, centralized standard of language, and everything can communicate with it. On the bottom, you've got different languages, different means of communication, where only part of that data has to go from one node to the next. But still, they form a network that is able to do the same type of work. Now, I say same type of work, but of course, these can serve different functions. The point here, though, is that you can go anywhere from fully standardized, same data formats, in a matter of degrees, down to something that becomes more and more different. And these serve different functions, both in the case of machine learning and in the case of the models that we use. Federated learning is very much like the federated models we have in BIM, and parametric models as well, where we adopt the standard and work with it. Transfer learning, that allows you to take data, or rather a model, from one network to the next, communicating only the parts that are necessary, is very similar to the kind of thing that Speckle does. Now, each has their own merits. They're different. One, you might say, is more efficient, and that's particularly good for late-stage production. The other, you might say, is more flexible. Now, in many cases, that can be good for early stages where you have to search, where you have to explore the space of design a little bit more. But in both of these cases, even though you may have degrees in between, this is only one dimension, I think, that's relevant. In both of these cases, we're still dealing with a communication that happens by transmitting the model from node to node. And there's another way of communicating, which of course is not to exchange models, but to exchange the data itself and the instances. Now, this is particularly what federated learning was meant to avoid. You don't want to transmit data, both for bandwidth and privacy reasons. But in some cases, that might be the sort of thing that is more necessary. So as an example of machine learning, anyway, that probably most people are familiar with, look at DeepMind's Alphago, which became the world champion Go player, to everyone's surprise, about 5 years ago or so. Now, I don't want to go into all of the details, but I do want to draw attention to one particular part of how Alphago works. And these are the diagrams from the original Nature paper 5 years ago. There are several different networks involved, but in particular, there's a kind of conversation, you might say, between what's known as a policy network and a value network. The policy network predicts, or rather is trained to identify the best move in a particular game situation. And the value network is trained to identify how valuable any given move is meant to be. But over the course of training, it's quite important, there are actually many different versions of these, particularly the policy network. It's actually trained by playing on previous versions of itself. This avoids overfitting, but the point here is that you've got different data that's involved. So you've got many different networks, but they're all communicating by producing and reading states of the board, actual instances of gameplays, actual games or particular states of games. This is the data. And this is what's passed around from network to network in the training process and, of course, in the process of play. These develop an implicit model of that data. And there are many different models, particularly important in the different policy networks that play each other in training. Now, that's Alphago. Of course, that developed over the years as well. Alpha 0 and eventually to Mu 0, which plays many different types of games. So this is a little bit more complicated, a little bit more generic in that it can play many different types of games, but it also is model-free in the sense that at no point is it actually given explicitly a model of how the game works. It can learn chess, or it can learn shogi, or it can learn an Atari game in the same way just by looking at instances of the gameplay. Now, each of those models that it might construct by looking at the instances, it understands the game structure, the dynamics, the value of any given move and the reward it might have. It understands all of this because it learns it from the examples itself. But the models that it builds, these implicit models, are actually incompatible with one another. Chess and shogi and Go are very different games, but the same kind of structure can be used to build any of them. Now, the point here is that, again, we're going from the same data format, everything tuned for Go, with a rudimentary model of how Go works in Alphago, all the way to Mu 0, which has different data formats and can learn different games. But in all cases, you've got a communication between one network and the next that isn't via transmitting the model directly, certainly not by standards. It's by producing instances of the game, playing a move, and then another network looking at that for its training. So in this case, we've got exchange via data and instances. Now, the reason I'm showing Go is because it was touted at the time and still as an example of potential machine creativity. In particular, over the course of the tournament with Lee Sedol, there were a couple of moves that were really quite relevant. Some of you might remember in Game 2, move 37 was a particularly surprising one. At this point, Lee Sedol actually had to he left the room, had to compose himself, had to take about 15 minutes before he played the next move. And he said afterwards, "Yesterday I was surprised, but today I'm speechless." Really surprised by this kind of move. Another commentator, a professional Go player, Fan Hui, said, "It's not a human move. I've never seen a human play this move. It's so beautiful." So here we've got a move that was really surprising to all of the human players, but it was the move that turned the game, and it was the move that effectively won the game for Alphago. Later, in Game 4, which was the only of the 5-game tournament that Lee Sedol actually won, the human player, move 78 was commented by Michael Redman. He said, "It took me by surprise. I'm sure that it would take most opponents by surprise. I think it took Alphago by surprise." Now, the point about this is that if Alphago can legitimately be said to be surprise, it's because of how those moves both looked to those networks that I told you about, the policy and the value network. And they both look very similar. even though one was played by Alphago and the other was played by the human opponent. But they look similar to Alphago in that the policy network, the network that's designed to predict what the next likely move would be, determined that this was about a 1 in 10,000 chance of being played. Very, very rare move. Both of them, very, very rare moves. But AlphaGo played its move, number 37, because the value network said it was such a high value. Of course, in Lee Sedol's move as well, it was also completely unexpected in this policy network. So in both cases, what we have here seems to be almost a contradiction. Something's very, very rare, but also something of high value. Now, in most academic discussions of creativity, most definitions of creativity, this goes back to Herbert Simon anyway, creativity is often described as being a combination of something that's very novel and very useful. And of course, these can sometimes seem to be at odds with one another. They can seem almost contradictory. But what you got there is exactly what we see here. Very, very novel, very unusual, these moves, very rare, but also incredibly useful in the course of the game. But this kind of almost clash, this contradiction in the novelty and creativity is the kind of thing that you can only get because you've got these two networks that are evaluating different things and communicate via those instances. I want to give another example of actual design creativity here now. And I've spoken about this project many times before because I think it's a very good example of the same kind of thing playing out in an actual design situation. This is a project by Anthony Gormley, one of his expansion pieces in which you can see the shape of the body, I think, in space, just in the center of this. But the sculpture is an expansion of the skin of the body outwards, about 60 centimeters uniformly in all directions. And it makes this very complex pattern of steel rods that takes a lot of time to put together. Now, my role in this was to try to figure out what the geometry was, to come up with the algorithm that would place these. And you can see as it's put together, this is the process where you've got this sort of open polygon network on the body itself. Each of those nodes has an expansion outwards, and then it's capped off by another series of open polygons. Now, to think about the geometry of this, I thought immediately, and most people do, that the geometrical description for this would be surface normals. So at every point on the body, you've got a perpendicular line that extends out 60 centimeters, and that would give you the overall structure. We could easily put that into CAD and we could figure out how to use that to improve the process, to fine-tune the process of putting these together. Now, of course, that's got a problem. It's got several problems, particularly in that the rods don't actually meet very nicely, particularly where the surfaces of the body are less than 60 centimeters apart, between the arm and the torso, between the legs, the shoulder, the head, and so on. So it turns out, in fact, that surface normals won't do the job. I'm making a very long story short, but there's another entirely different algorithm that gets all of these pieces, and particularly these surfaces between the legs, the arm, and the shoulder, and so on. And that's a Voronoi diagram. So here's a set of points. If you're familiar, most people are probably familiar with Voronoi diagrams here. The Voronoi diagram represents the area around each of those node points that's closer to that node point than to any other one. So these red lines are bisecting node points. Now, if you apply this in 2D, this is what you get. If you apply it in 3 dimensions, using points on the surface of the body, you get both that internal sort of honeycomb structure, you get the lines extending outwards as the boundaries between the cells, you get the outer surface if you cap it off at about 60 centimeters all over the place, and you get these planes, these nice curved, graceful honeycomb surfaces between the legs and the arm and the torso and so on. Now, the point about these, though, is that surface normals and a Voronoi diagram are entirely different descriptions of what seems to be a very similar geometry. But they are entirely different. And if we think about how the design process actually goes, in this case, I say it's much, much more complex than this, but to simplify it, we went from sketch models, real sketch models in the world, to this idea that there are surface normals, an instance to a model of surface normals. From that, you can construct some more, you can make them, and you can find that the rods don't meet up very well. And from that, we can go and abstract totally different idea of what this is, a Voronoi diagram. Now, the point is, we're going back and forth between the real physical things and these machine representations or these abstract representations. But when we go from one to the next, the surface normals to the Voronoi diagram, there's no way of transmitting, there's no way of bringing one model smoothly into the next one. They are entirely different. So the difference between one and the next is actually a creative leap, a very important one in the case of working out this particular geometry, because the Voronoi diagram, in the end, is the one that meets the intuitive idea of what this sculpture is supposed to be. But the point is that you go from one to the next, and they are incompatible with one another. Now, there are other types of models. Here's some current work. Aurora Lee has just sent me these images on a project we're working on to understand the geometry of a basking shark, or the anatomy of a basking shark. But our data sources are so varied. We've got this particular case, we've got YouTube videos, and we're trying to reconstruct using photogrammetric techniques what the 3D image is, what the 3D structure is of the shark. But we're also combining that with CT scans and laser scans of surfaces from different species, from different samples of basking sharks, to try and get a model that is something that can reconcile all of these very different data sources. Now, in another project, Giulio Brunaro's PhD last year, which I believe I may have mentioned at the conference last year as well, where he's trying to teach a robot to use a chisel on wood. Very, very complex task. But starting off trying to understand how a human might do it, and then transferring that data to a very different body. A robot's body is very different. A robot's brain is very different. There's no way of taking that information directly from a person who carves into a robot. Just as there's no way directly of a craftsperson transmitting that data directly from brain to brain into an apprentice. The only way to do it is, first of all, for the robot to start imitating, but then to do it itself, to get feedback from the process and to learn over time, and to develop a model from instances of actually doing the thing. This is how the communication actually works. So we've got different ways of working here, both in machine learning and in our representations in CAD and computational design. On one hand, we've got models that are much more standardized using the same data format, which, as I said, are good for late-stage production, perhaps. On the other hand, we've got different data formats, which are good for early-stage search. Now, we can deal either with models, or we can exchange data and instances. In the first case, where we exchange models, particularly if we've got a case like federated learning or federated models, each node can protect the data that they have, and this is very good for security. If we're exchanging the data, however, obviously we can't protect the data, we have to exchange it, but this can be better for exploration and creativity and those creative leaps that I talked about. Now, as I mentioned, there's no hard and fast line between particularly the same data format versus different data formats. That can be blurred in stages. And many applications, of course, Alphago is much more complex than this. There is some transfer learning. There's some exchange of models that goes on as well. Every application might take different parts, different quadrants within this diagram. Giulio Brunaro's chisel robot, for instance. On one hand, working with a new chisel using the same data format, it can slot that into what it's already learned, and it can tweak its model a little bit. But in terms of transferring learning from a human, which is very different to the robot, well, this is certainly a case of using different data formats. In general, though, my point is that there are different ways of working, both in machine learning and modeling, for different purposes. And we should consider them when we have those purposes in mind. So on one hand, you might say toward the lower right, we've got ideas or ways of working that are very good for creativity. Toward the upper left, we might be better at clarity or indeed security. There is this variety, though, and that's important because we have lots of different things to do when we're doing computational design. Sometimes we have a priori structure. Sometimes we can take them as given. We can have our standards of communication. We can have our standard models. We also have similarities in our brains. Just like similar models can communicate, we have standards of perception and cognition. I'm very much looking forward, although I'm pre-recording this, I'm very much looking forward to the cognition session in the conference, which will have happened by now. And sometimes, of course, we need to change our structures to have a paradigm shift, to have a creative leap, we do have to look at things in a different way. And sometimes these can be useful in design as well. The point here, though, is that the approaches to models and data that we have in machine learning very much parallel those that we have in design computation. These are two fields that I think can work together and can learn from one another. Thank you.
Thank you, Sean, very much for this amazing keynote, this closing remarks.